Yeah, so we talk about Transpile circuit. Yeah, and then we talk about optimization levels last time. And yeah, last time I found my notebook was incorrectly erased. I was going to talk about this pass manager. Um, and we ended up going to the website of the documentation, but it actually was one that focused more on the optimization level. So there's another one. Let me see if I can open. There's not a notebook which is actually a notebook on Transpile with Pass Manager. You can get it from the documentation. Somehow some of the notebook when you download, it complained that there's no metadata. So, but this one you can load it. Yeah. So Transpile with Pass Manager. So they introduced the idea of what is a pass manager. Yeah. So this transpilation is a process to transform a input circuit to one that can be run on a quantum device. So this occurs in the sequence of steps. It's called they call it they call these transpiler passes, and each pass handles something in particular. And an output of one pass can be the input of the next one. And they can be maybe repeated and in different combinations. So the one example, one could pass through the circuit, merge all the consecutive sequence of single cubic gate. So you merge single cubic gate, the next pass, synthesize this into the basic set of target device. Yeah, a manager is one that manages these different passes. Right. Yeah, you create pass manager by initializing a pass manager, this class with a list of processes, and you run the transpilation by calling the run method. Okay. They have some abstract uh notion called stages. Um, I can maybe go back to my slides. Yes, there's 6 stages. So initialization or initial passes to run before embedding the circuit to the backend. Layout, you map the virtual qubit in the circuit to the physical qubit. Routing, if you have swap of something, then you need to route. Translation, this is translate the gates in the circuit to the backend's gate set. Optimization, yes. So they will optimize according to some cost. Optimize would run in a loop until convergence is met. So might be you want to minimize the depth. Scheduling, this is hardware aware passes that schedule the operation in circuit. So you would create some schedule which run first, which run second, etc. Yeah, so these are the abstract stages. Okay. Yeah, last time we used generate preset pass manager. Right? So you need to input the optimization level, which backend you use. So here we use IBM Brisbane. To do that, you need to create a circuit. So this is 2-qubit circuit. It's a Adama on A and C naught AB and then reverse C naught. So maybe one should first bring the circuit. To see what was the original circuit. So this is the original circuit, such a simple circuit. And then you want to transpile to the machine of Brisbane. And because we use the preset manager, we only say optimization level 3, and this is what it gives. So this is C naught, it decomposed into something, and then C naught here. And this is Hadamard, it get transformed into something like that. There might be a combined combination there. Yeah.
What's the ECR?
Yeah, this is echo resonance gate, or echo cross resonance. This is you can see the device and see what the 2-qubit gate they have. So let's click this one. It not necessarily use ECR, so it use Control Z gate. There's also RZZ. That machine is Brisbane. ECR. What you can do is go to the documentation. Qiskit learning, and it will tell you what the form of that, more detail about this. ECR gate. Okay. Echo cross resonance gate. This gate implement this IX minus XY. And you can use this to, okay, this is the matrix. You can use this to construct a CNOT. So let's see if we use a different machine. Like we saw this machine. Yeah, so if we use this other machine, right? It has these CZ gate, and so we can use this machine and see what the Transpile circuit is. It would use that gate, right? So let's try. Try other. Okay. Okay, let's try this one. And you will need to say backend equal to this. Just say, give it a different name. In order to do that, we'll need to call this the different path manager is specified to this backend. And let's transpile this. Yeah, I'm just giving it a different name. So there's a difference. Okay, so let's see what it is. Oh, yeah, you're right. Let's use this. The way we were doing the same thing before. Yeah. So it used Control Z gate, but you can also, yeah, without going to the website, you can just say backend. I think is basis 8. Their estimate. It's a list. Yes. Yeah. So you know what the basis gate. Here we can bring the basis gate. Yeah, so this ECR. It's different. It's short here. It has RZZ shown here on the website, but it does not show on the, when you print that out. It's missing a few. Control Z identity RZ, XX, and X. It's missing RX and RZZ somehow. Okay, so yeah, the next one is create your own path manager. So you may not want it to optimize in the way that is designed by Qiskit. You want to design your own way. Yeah, to do that, you just import path manager, and then you need to import a few passes method. Collect all the 2-qubit block, consolidate blocks, unitary synthesis. And you can say what the basis gate you have, this, and then it has another equal translate and path manager. So what it want to do is collect 2-qubit blocks, consolidate blocks, and using the basis and unitary synthesis. Okay, so we just construct this path manager. Okay, so this is using also the same thing as before. Yeah. So I don't know why it need to use the same. Why does it need to create the code again? Yeah, this is basically the same. So let me not run this. Now this is translate, and according to what I want to translate. And the path manager uses 3 different passes. It called this translate, collect 2-qubit block. So it will collect this, consolidate blocks, and unitary synthesis. So we combine and then decompose in some way according to the according to this basis gate R X R Y R X X. So you see all the gate will be R X or R Y or R X X. So this is how you decompose into one that will be run on the circuit. Okay. This is create your own pass manager. A stage manager's pass manager is also composed of individual stages defined by a pass manager. Okay, so what the translate here is still a pass manager. It's not a stage pass manager. The stage pass manager has a few pass managers. It's like a layer structure. Okay, so you create that by specifying the design stages. The following code for your stage manager, which has two stages, init and translate. Okay, so init is a pass manager composed of the above unitary synthesis basis gate, minimum qubit equal to 3. You need to see exactly what this min cube 3 is. I would suspect that you only have gate that are 3 qubit, and then the next one will be unroll 3 or more. So what unroll is you have 3 qubit or more qubit you want to decompose into 2 qubit gate. Okay, so this is a stage pass manager. It contain, yeah, when you define a stage pass manager, you need to have define your stages according to this keyword init translation. So and you have these init, init, and then translate that you define earlier, and you define init. Yeah, this translate has also unitary synthesis. And somehow you could have similar actions used in two different pass manager, pass manager, and then you can put all together in the stage manager of these two individual ones. Okay. There's no limit on the number of stages you can put. Another useful way to create a stage pass manager to begin with a preset stage manager. That's what we have been using. And swap out some. Here it does not actually run this. It does not actually run this. Yeah, so these next two, it didn't run anything. But let's see if we can run on this circuit. But we only have 2 qubits, so maybe let's have some 3 qubit gate. So we have 3 qubit. Okay, if you want, just call it ABC. Let's have another one. In between, let's just say it's between A and C. And let's use this stage PM, run the circuit. Transpile. And you need to say display, otherwise it will not show the circuit. Transpile because the typo. Okay. We could have maybe control Z. Okay, maybe this is more interesting. You have 3-qubit gate, right? And then transpile, and you see it's much longer. Yep. Okay.
Is it translate a default transpile way or
I don't know the default. I think that yeah, the default would have all the 6 stages. Use the preset manager. I don't see whether we can get any information. I don't know whether we can. Okay, if we say print, let's see. Okay, it's the same as this one. And I don't know this object has any. Let's see, can we say what is the passes? I don't know whether it has this keyword. Can we print out its it's an object pass manager. So it's so it print out its pass manager. But to know the detailed information, translation, it's a pass manager because you have 6 stages. You also have routing. These are the keyword that you input, right? So this would be like routing equal to something, my routing pass manager. Okay, but yeah, how do I print information? It's the input. How do we print
can do pass manager dot passes?
that passes? That's what I did and didn't say. It doesn't show
Oh,
in
sorry. Pass manager dot status.
the stage. Oh, okay, that's useful. Yeah. So so you have all these, right? But to get more information, uh, I don't know how to retrieve that, but you might be able to do that. Maybe it's some Python programming language, may be able to. I remember something, but let's see. Maybe in our basic Python, we can programming that if you know how to retrieve, I think it's
Hello, Professor.
okay. You know how to do that?
So as far as the documentation shows, there are three attributes that we can access. The stages, the expanded stages, and the third is the invalid state register. So maybe that's not relevant. So maybe we can try expanded stages.
What can you
It's there in the chat.
expand the stages? Okay. Yeah, but yeah, we can always see the documentation. So at this point, I was lazy, didn't go look up. Yeah, I didn't go look up, but you can. Yeah. So they are INIT probably has these, right? And then layout has these. Routing has pre and post. Translation has pre and post. Optimization has pre and post. Scheduling has pre and post. Yeah. But to get useful information, you have to go to the documentation to see what is a preset manager. If you don't input any parameter, you don't swap out and pass it. What are the default? Okay. Yeah. But this will be covered in the lab one if that was chosen. Okay. So the last part, another useful way to create pass manager. Yeah, this way is and swap out. For example, the following code generate preset pass manager with optimization level and then specify a pre-layout. It's right what we already call the preset manager. I'm not sure about the three. I'm not sure about the three here. We can go look up. Yeah, but there was something about the three above. Also,
Label.
oh yeah, three. Yeah, I forget. It's used. I think it's a good practice. I say it would be good practice to just put in that options. I think it's a good, yeah.
So the pass manager here is a stage one or
Preset pass manager.
it's a stage the pass manager?
I think we can see this, right? You call it stages. What is that? Oh, backend equal to.
Yeah.
If I use the keyword,
Yeah.
and I should use keyword here. Pass manager is not defined because typo. So this is a preset. Then this is a stage pass manager. If we go up, and we have created a translate, right? We have translate. You can print stages and see what it does.
Yes. Title.
Trans. It has no object. It's only the pass manager. Yeah, you could also print. You can also print what just print this and see what the object is. It's a pass manager. It's not a preset. Yeah. So this is also the other one. We can also do that. I think all these are good because we are just. This is how we learn things. Okay, how we learn this is by playing with the code. Is a stage path manager object. You could also ask is I remember with Python this is instance let's say path manager next stage path. It automatically turn on. Somebody's remote. But I see. So path manager is a stage path manager. Right? And let's see, is it is this pass manager also a pass manager? It's just really just looking at whether how they define the classes. True. So, but then the other way around, like if we say translate, that one would not be a pass, stage pass, right? So you can see just by asking this, you know that the pass manager, this one is a stage pass manager, is also a pass manager. And this translate is a pass manager, but it's not a stage pass manager. So there is a maybe some class translate a stage pass manager is a descendant of a pass manager. It maybe use that class. Well, this is Python. I'm just playing with this. Okay. This one here has it calls a preset pass manager, which is a stage pass manager. If you want, it should be preset stage. Okay, then you define inverse gate list, this H or X. Okay. HK is cell, so it doesn't need to. This one is a tuple, so indicating the gate and its inverse. The gate is inverse, the gate and its inverse. Logical operation. Pass manager, CX cancellation. There is a pass manager and want to try to cancel control X gate. Inverse cancellation, if you have a gate that are defined here as the inverse, they will cancel to identity. So you want to have a pre-layout stage, right? So we have a pre-layout and post-layout. So yeah. So these will be useful for more complicated circuit. Yeah, so for these 3-qubit and 2-qubit, you don't see much dramatic reduction, but in a larger circuit, imagine that there will be substantial reduction. Okay, so this finishes our discussion on on pass managers. So any questions? This is as much as I know. Yeah. If I can also point you to documentation. So if you click this, it will go to documentation. That what we should have done. Yeah. Okay. And there's also a video pass manager. It might be one of the summer school lecture. So let me open it.
Is that we
Okay.
we wrote this
This means
algorithm
I
in
have
Rust,
watched
and we
this.
can take advantage of. Okay.
Actually, that's the
Today I'm going to
second
be
time.
talking about quantum circuit compilation with Qiskit.
So these
Before
are
we dive into
one
it,
of
I
the
wanted to make a quick note on
one of
terminology.
the nine
In
lectures.
Qiskit, the quantum circuit compiler is known as the transpiler.
Yeah, so you can watch these video. You have the link. You can watch these video. And we might come back to refer to these video, the content later. Okay, so I'm going to close this one and come back to the slide to see what I have prepared for the next one. We already did the path manager. Similar. Okay, so next, I'm going to discuss the simulator in more detail and Qiskit runtime primitive there in more detail. Yeah. So for this, let me see. So there's also documentation. Let me click the documentations, and there's an introduction on the to the primitive. So let me show the page. You click. Yeah, because I have to share the other ones. It takes some time. When you click, it will go to that. This introduction to primitive. Okay. So base classes, base estimator, sampler v2. So these base classes, and you will define other class that use this base classes. So now they emphasize the v2. The v1 were the initial design, but they're going to remove that. So in the future, this v2 may also be dropped, might be dropped. So Qiskit runtime primitive, yeah, implementation of the primitive base classes. Estimator v2, this is from runtime primitive. Estimator sampler. In the simulator, we use state vectors. Estimator, state vector, sampler. There's also back-end estimator and back-end sampler. You use this to classes to wrap any quantum computing resource into a primitive. This let you write primitive style code for providers that don't yet have a primitive based interface. Okay. Okay, so I'm not going to talk about benefit. Okay, and then there is also the video. Let me show. Okay, there's also the video. If I click, see, there's also the video. You see what video.
So there's 4 different strategies supported by the sampler
Okay.
and estimator in its current
Right.
form.
You see that I
Programmed in
definitely
an
want
environment.
these when I prepare. So the lecture also have one runtime primitive. Okay.
What do we do with the primitive?
Primitive, there's a estimator, right? And there's a sampler. We used to run, and then we get the statistics. Now they don't want you to use backend.run. They want you to write that in a way using estimator and sampler. So you need to, in the way we say run, now we need to use sampler in order to get these statistics. And estimator is for you to estimate an observable, like a poly. We talk about these operator, so you can use estimator to estimate observable.
So it's not for a real machine.
No, this can be used for real machine, and can also be used for simulator. Yeah, so maybe I can talk about the concept and then show you the code. But there's also another video. So these video were official video from IBM. There's also somebody from Los Alamos. I can show. It's called. His name is called Diego Emilio Serano. It's from Los Alamos, and he also has a set of video. Control click. Let me click to. Yeah, so he also has a few video, which is very nice video, setup video. Yeah, see this. So he has a setup video talking about these similar primitive, and so for each video he has some short notebook. So let's maybe follow some of the thing that he used. Yeah, so my material combine a lot of code that people have. Okay, so let's come back to the slide for a moment and explain the idea. So you see from the diagram, sampler will give you some distribution of the outcome. And what you do is we used to use backend and run. But now you have to define a sampler and then you say sampler run. For the circuit that are transpile and maybe number of shots and other maybe parameter if you have parameter. For maybe the circuit that has parameter, you need to input the actual value. And estimator is to run a circuit and with some observable. Yeah, so sampler you would have measurement. For estimator, you will not have measurement. You only write the circuit and you say what observable I want to evaluate, and Qiskit automatically process that. You don't even need to worry about how many, like we have the X operator, Z operator need to evaluate. Here, you just say X and Z and it would automatically do it. Or you just write Bx times sigma X, Bz times sigma Z, and automatically it would evaluate that. So under the hood, how it deal with that, we don't need to worry about. So it's really packaged in a way that you don't need to worry about detail. But if you want to design something, you might want to try those on your own and then you know the process. So, but we demonstrate how you design that in the VQE. Yeah. So sampler output a probability distribution over possible measurement outcome. The circuit, you need to include measurement because they would give according to what qubit are measured and where the classical information is stored, and they just print out those. Okay, estimator output is a value or a set of a list of values, depending on how many observable you have. Yeah.
One for states, one for energy.
You could have not a spin code. That's so you could have observable 1, observable 2. It could be energy, it could be anything. Yeah. So this is like a single job, right? And last time when we were using the VQE, we used session. Session allow you to run this circuit with this parameter and then classically processing and see what next you have. Batch is you run many jobs and they don't have these parameter dependence. Like you don't need to calculate to estimate next dependence. So you save time of this classical processing. You just run the circuit, immediately you have another circuit. It's easy for you can pack a few jobs. You submit. You don't need to wait. One job finish and another one. Okay. Yeah, so this is a summary that I took from Dr. Serano's slides on YouTube. So there are two types of primitive, but this one is already deprecated. So you don't need to worry too much about it. But in some of implementation, like in the community maintained Qiskit algorithm, so far they're using the V1. So some of them you need to update in order to run on the machine or use the V2. It does not have the capability of V2. Yeah, so there's some differences between V1 and V2. It's just how you put in the argument. There's some slight difference. Okay. So his suggestion is don't bother to use V1. But there are codes somewhere that would have V1. Okay. And here's the diagram that he has about where you have these sampler estimator in the Qiskit. You have provider, basic simulator, you have primitive, you have these, we have seen these state vector sampler estimator. In Qiskit Air, it's a separate package in addition to Qiskit. And there are also primitive air simulator, okay, sampler estimator, but these are V1. The air simulator will have state vector, different kind of simulation. And also we also saw on the documentation, there's a primitive IBM runtime primitive sampler and estimator. And a V1 and V2 version. And so he says, don't worry about V1. Okay. So I think the best way to learn is to run code. So I have already uploaded code into the Brightspace. Let's just look at few codes. I don't know how many we can cover, but I think I uploaded 4 notebook. And let's take a look at these. Okay, we were at the Pass Manager and I uploaded supposed to be the 06 lecture or the 7th lecture. But this is our 4th week, right? 4th week. Yeah, assuming each week we have 3 hours. At the end of today, we will have 12 hours. And their summer school only have 9-hour lectures. So we have gone over the time that they have, but we learn it so maybe more slowly or different aspect. Yeah. So I have put a link of the video of Serano, Dr. Serano's YouTube. So this is this one. If you click, this is this. Not the ad. This would be this one.
Different ways in which we can simulate circuits locally using Qiskit,
Okay,
and
I'm
also
not
how we
going
can
to
execute.
play this. You can watch this on your own. Or maybe I could replace all my lectures by playing the old video. And I just pause and comment. Okay, so you import quantum circuit as usual, and then Qiskit info, call it QI. And this is the 2-qubit circuit. You have singlet, as we have. And you can say QI dot state vector QC. You would output this is a simulator. So this is quantum info simulator. So he talked about quantum info simulator. The quantum info simulator, you use the state vector, would show you the state vector. And I said, mentioned earlier, you can just use LaTeX, show you the LaTeX form. It looks nice. This is singlet. Okay, and in this corner info simulator, you could also show the probabilities if you measure, right? Of course, there's a limitation of these simulator because this classical simulator can only simulate up to a few numbers, a few qubits. Okay. Okay, I am just here. I'm just suppressing. If I do these counts, so you could also from the state, you could also say sample counts. And I have shots this many. Okay. And I print this because I want to suppress these MP.string. So that's why I have these extra line. So I want to suppress so easier for me to read. Yeah. It can also, once you have the count, then you can just use a plot histogram. Okay. So this is we sim this before. We sim this here and there, but just combine all these together. This we probably didn't see that before. So this allow you to simulate, right, the experiment and then collect the count. And here, state that sample memory shots number 10 is preserve the sequence. Like, okay, the first time I got here, let's see, if I print this, it may be different. The first time I get 0, 1, second 1, 0, etc. It just keep the history, simulating. Okay, if you were doing experiment, this is what you record in lab book. Okay. Here I define a operator. We talk about this sparse poly operator. This is how you define these 2-qubit operator and how they add together. Coefficient. So I bring this. And yeah, so I can, if I can use these 2 operator to make it a matrix form, and I draw it. So this is showing you the poly operator. Okay, and if you have a state side, quantum info state info simulator also allow you to do the expectation value with respect to these. Yeah, all with respect to psi. Yeah, of course, this is like almost exact. Yeah. I think I just say you could also draw blocks of here. Yeah, you could also draw blocks of here. It would draw the reduced density matrix. And you see there's nothing you see because it's at the origin. Okay. You could also, the quantum info also has a density matrix. You have this QC. QC is the circuit, circuit. Psi is our state vector. QC has been our circuit we define, and you can convert that to a density matrix. Right? It's a single state, right? So it's either block. I just use LaTeX draw. You can draw different way. We showed these earlier. City. So show the imaginary time. Imaginary part, real part. You could also trace over one of the qubit, right? And when you trace over, it becomes a diagonal matrix. So that's why when you use the block sphere, it's at the origin, so you don't see anything. And we also see that we can use operator function to convert that into a unitary. A circuit is a sequence of actions, gates, so you can also convert that to a unitary. Yeah. Okay. So, and there, Here's another example that introduce measurement. So previously in our circuit, if you use state vector, you don't put measurement in the circuit. And here we explicitly put measurement at the end. And here I just give you an example of CF. So I have Hadamard on the first qubit 1, and I measure it because I put in superposition so I could get 0 or 1. If it's if 1, see if I think would be the classical register 1, because I measure qubit 1 and store in classical register. This is classical register 1. If the value is 1, then I do X gate on 0 here. If C1 is 0, X1, that's here. And then I measure 0. Okay. So you can also guess, okay, let's just say Hadamard will put 0 and 1, right? Superposition. If it's 0, it does nothing. If it measures 0, it will also do nothing. So it'll be 0, 0. But if it's 1, then I flip this to 1, right? So it'll be 1, 1. Okay. So draw the circuit here. But you see that when you do that, CF is deprecated. Will be removed in the version 2. We're still 1.3, so there might be some time to go before they remove this. Okay. I think, and if you involve measurement, maybe he did try that. If you have this measurement, then you cannot use any of these state vector. Right? So if you see, let me see state vector. We get this. Okay, let's see. So you can try and see if what we get if we try to simulate this. Let's say side 2. So it would say you cannot apply instruction with classical bit. This is from the quantum info package. Okay. And it's covered in the video. And this is the second video it has. So the first video is probably an overview. And I upload the second one, basic simulator, is we start with this. How do we simulate that? How do we simulate? Of course, we actually have seen this before. We actually have seen the simulation. We use air. I think we use air simulation. Okay, but you could use a basic simulator from this basic provider. You just say basic simulator equal to basic simulator. So this is the circuit that we say we just saw that state vector cannot be used to simulate. And here you can actually do that. You say basic simulator.run, shots, and then drop. This is just the usual way. It's not defined because I did not run this. Okay, and this is the result. I print the result. see the result as this. You could retrieve, you could get a count, by get counts, get count. Okay. And once you have the counts, you can print the counts, and then you can plot. Okay. Now it's printed. So it's printed here. So you can use basic simulator to simulate the one with measurement. Okay, so in the basic simulator, you can run the circuit, and with sharp 10, you specify 10, and then we say memory equal true, just like the previous year when we were running this to simulate history. Yeah, here. In the state vector, once you have the state, and you can sample and with memory. And this is something equivalent to that. So we only run 10 times, and you get result. If you get result, print result, get counts. It will get just the count, but if you say samples equal to result, get memory, so you retrieve the memory, then you get what is the sequence of the result that I get. This is like, yeah, you do an experiment. This is what keep the record, and we know the result can only be 0, 0, and 1, 1. But if it's noisy device, then you would have 0, 1, and 1, 0. Okay.
Sometimes you run some practice in the previous one, use the sample to get there.
So not yet. We have not get there, right? So here, oh, you mean this?
Yeah.
Sample memory. So you need to see how it was designed. But here we're still using the old-fashioned dot run. Simulated dot run. It does not complain that it's deprecated. Okay, so here, this just introduce the quantum Fourier transform circuit. Right? We have seen this on this from the Qiskit circuit library. This point is to show that if you use simulator and you say you want to run a circuit that has QFT, it does not know. So you need to transpile. So it says error, it does not recognize. So then we can transpile, and here we don't need to use complicated preset manager. You could also use that. You could combine what we just said. Preset manager, optimization level, backend we would be equal to simulator. Okay. Then you have a transpile circuit. So let's print the circuit. Print. This will be text, but at least let's see the circuit. Okay, this is ugly, but yeah. This is the circuit, unitary measurement. Okay. Now you can run because the simulator now know what the gate. This is unitary. We could print it in a better way. You see. Yeah. but you still don't know what unitary is from this. But the simulator would know the unitary matrix, so it can really just simulate. Or you could transpile with some basics gate set. Yeah. We could, right? Previously we have these transpile what kind of basis gate we want. You can also use that options that we covered here. You can combine a lot of things. Convert here. Right. Basis gate. Translate. Right. This is translate is we define the translate. You can use this basis gate. Okay. So that's that's another video. You can access the video. I think I put it, yeah, the link here. So that's a basic simulator. And there's a simulator that we have used is air simulator. So this air simulator, this notebook compare also air and basic simulator, and maybe also the state vector. Yeah. So this is the circuit that has been used previously with a measurement. Okay, this is just to review that you cannot use state vector similarly.
What's it like? State vector is like running the circuits and
It's doing the computation. You calculate the state.
That's okay.
You do it by hand. Yeah. Right. And basic simulator, it does not give you the state. It only give you the counts, right? These. So that we saw earlier. And so this notebook is focusing on the air simulator. So I import air simulator from the Qiskit Air. It's a separate package you have to install. Okay, so basic simulator does not get the state, and air simulator has the ability to get the state. So here, you have to say that I want to save state. So in the circuit, after this, we say qc.save state vector. We draw this circuit. Okay, you can actually get the vector, state vector. So let's just do this. So so I run this. I would follow the circuit. Sometimes I get 0. If I get 0, the state vector is 0, 0, right? So this is what's shown here. But there's a probability that you get 1, 1, right? So the state vector allow you to sorry, the air simulator allow you to save the state vector when you are measuring. Yeah, so that's a nice thing to have. Right. Right, so okay. Yeah, I did run a second time, so let me get the 0, 0 here. 1, 1 here. So if you run a few times, it will equally giving you 0 and 1. But it's doing this in sort of one procedure. You still have the result. You still can get the counts and then print this. you can still get the count and you still have the state vector. But the state vector would be whatever randomly obtained vector it has. I don't know, it's probably will be the last one. I don't know whether we could have memory. We might with it. I haven't tried this, but let's see the memory we saw. You can use memory, right, in the basic simulator. What if we say run shots 10 and memory true? At this. Okay. Let's just do 10. And memory. And I don't know whether they have this. It's just okay. So how do we get the memory? It's like some get mem samples get memory. So we could print. So the last one is 1, 1, right? So I am suspecting that the sequence, the 1, 1, they just use the last one. So this 1, 1 is before. Where is 1, 1? It's here. Oh, there's no measurement at the end. In order to get this is always 0 because we never measure the qubit there.
Oh,
So let's add another measurement to it. Maybe let's add a measurement. Let's add a measurement. 0, 0. Okay. If you don't measure that, it would assume it's 0. Right, so we always get 0. Let's try this. Okay, now it's the correct one. Right? So this also shows that you have to be careful when you writing this. You may assume you measure 0, but you didn't specify that.
what's one? Sorry, say one.
Remember we say if it's 1, it would flip this.
Yeah.
And this was 0 and flip the 1. Right. So it should.
But why not one plus 0, 0, 0?
It's not superposition because you perform measurement and then you do that. Do classically flip. Okay. I think our time is up. But I'll finish this one, right? So I'll finish this one. Oh, why do I have another measurement drawn here? Oh, because I was using that and then I run this circuit again. So that's why. Let me, show the correct. Show this here. Okay, if we do that, I'm just going to run this so that there's only one measurement here. Okay. Yeah, here is creating a really large circuit and equal to 100. So let me just do 10. And this is the circuit. So here, he was trying to compare the two simulator, the basic simulator and the air estimator says one is this and the other. I think from his run, he concluded the air estimator is more efficient. But on my machine, running this, okay, let's do like 50. It looks to me from this result, I'm comparing the two simulator. Okay, what is that? Oh, still waiting. Oh, I should not draw this. I should not, when I have 50 qubit, too many qubit. Let me just plug this on.
Also, basic only can do.
And basic can only do like, I don't know, this 24. Okay, so 20, we can just compare time. So different way of simulation. Somehow it was very efficient, just once. So you see, so air would be better when the notch, the qubit number is large. And you could also use a matrix product state. It's when it be 100 qubit, then you can use matrix product state. Yeah, the following one is for noisy simulation. Okay, so it's quite short, so maybe let's finish this part. Because the coding is almost the same. Okay, you have a circuit. This is the ideal. Okay, it's still ideal simulations. Okay. And now we introduce noise. So in order to do that, you need to import this noise. And then you can say define what kind of noise model. Like we learn depolarizing error model, probability. This is two. I suspect it two qubit, or I'm not sure. So yeah, because we have 2 qubit circuit. So you can check that. But assuming it's doing these deploying channel and noise model, you just say noise model. You create this noise model, you add all qubit quantum error. This is defining this error on CXK, and then basis case. So then you do the simulations. In the air simulation, you can pass this noise model as a basis. Oh, you also have basis gate. Right? So previously, we could also use basis gate when we transpile. And you get count, and this is noisy simulation. So you have additional incorrect results. Okay. Okay, so that's it for today. So we didn't finish. I think there's a fourth one. Was there a fourth one? I probably these are the 3 that I uploaded. The next one I'm talking about. Maybe there's one more, but we can finish this last time. Next time. Yeah. Okay. So I guess that's it for today.